Another topic for today is called collections, and I will tell you about collection interface and sub-interfaces of this interface or extending interfaces, different implementations of collections, about iterators, and a little bit about sorting and ordering using comparable interface. And I will mention also comparator interface, but I will not explain it in details. So, collections interface is a common interface which is used as a common API, where API means application programming interface, to deal with multiple elements into single unit, into a single container. And it has several sub-interfaces. It's easier for me to explain this class diagram. So here we see class diagram which doesn't follow UML standard properly. So that means even Java designers and documenters sometimes cannot use UML properly. According to UML, what is closed and colored arrow here should be closed but not colored arrow here, and what is dotted line here should be dashed line, and what is closed and colored arrow here should be open-ended arrow. And because of these things that they do not follow UML standard, they have to explain that this arrow means extend and this arrow means implement. And everything else is correct here, but arrows are not correct. And there are two different interfaces on this collection API. One is called collection and one is called map. Where is difference? Map is collection where you have pair of values. One of these values is used as a key or index, and another is of course related to this index or key as actual value. And collection is interface which uses just single value, and single value itself is used as a key to identify its uniqueness, to sort it, to search for it, etc. And both of these interfaces are not related to array at all, so these are independent interfaces in Java API. But these collections are just extend Java object in general, but some of these implementations of these interfaces may have arrays inside it as a data structure to hold values. Remember that similarity between collection interface and array is the same as similarity between string and array of bytes. There is array of bytes inside string, but of course string is not the same as array of bytes, because definition of class is completely different. Possibilities what you can do with string is much more different than possibilities what you can do with array. But because string is array of bytes, this limits what you can do with string, and one of these things is that string is immutable object. If you want to change something to string, you can change it and you can forget about it. If you do not want to forget about it, you need to reassign this changed value to the string again, because you need to recreate new array inside it. And then about these features, interface describes what kind of API, what kind of features your collection or map supports. If it's map, then it allows you to use one value as a key, another value used as an actual value, and then it may be also sorted map or navigable map. And this means that it also allows sorting and navigation forward backward in this collection. If this collection interface is actually set, so set extends collection, then this is set of or collection of unique elements. You may have one null element inside this collection, only one, and all other elements should be different from other ones. If this collection is actually list, then it allows you sorting. And if this is actually queue, then this is some kind of list, but particularly for priority queue, you can also add priorities to this queue. For example, how some of elements are more important than other in this particular collection. And then you should know something about implementation of these collections, because implementation influences heavily what is good and what is not so good about these collections. So first about map. Map cannot contain duplicate keys, so this value should be unique. This value as a pair could be anything. And it allows you to do put new pair of keys and values inside it. You can search for it, you can check does it exist, and you can add many keys, pairs of keys and values together. And mostly used implementation for map is hash map or hash table, which is hash map but thread safe. So it's slower, it uses synchronized methods. We will talk about synchronization in details later. So you use it if you want to access the same collection or map in this case from concurrent threads. And hash is specific function which takes any arbitrary input. And in computer science, hash functions are usually shown as two-dimensional funnel, piltuve in Latvian, no idea how in Russian, and you may see H letter inside here. So here, as an input, you can get big arbitrary data, and here you have pretty small number. How small this number is, it depends on hash. It may be, let's say, just 4 bytes in size here, 100 bytes or whatever. And what is important feature of the hash is that for the same input it always produces the same output, and for different input it produces different output except collisions. For if this number is very small, and here you can put everything in the world, then of course sooner or later it may happen that different inputs have the same different output. And this is called collision, and this is considered bad. But in most of cases you can ignore collisions, and you know that if any single bit here, so you have a large block of data, let's say in binary zeros and ones, zeros, ones, zeros, ones, zeros, ones, and if one single bit changes from 0 to 1, good hash function is following that probability of this output, for example it has just 8 bits here, probability that each of these single bits will flip to opposite, like 0 to 1 or 1 to 0, is approximately 50% chance. So that means that you can put just one single bit here and then push it through this hash function, and this single bit will be somehow diluted to entire output with similar probabilities with all of these numbers. And similarly, if for hash output one single bit is changed from 50 to 50, then probability that for this large input each of single bit it also has 50% chance that it should be different. Then again, this means that for one single bit here, when you take it as an outside, it actually takes its input value or is diluted in all these bits inside hash function. So from this direction, one single bit influences all bits in output, and one output bit is actually influenced by all input bits in the input. So one bit to many from single bit to the output, and when you look on one single bit to the output, all these bits are considered into input. And it just makes shorter, and such hash functions are used very widely to check consistency of data, because if you have some large data like DVD disk or CD disk or movie, and you want to check that nothing is tampered and everything is fine, you can create a hash value for it with some hash function, and it will be much shorter than this big CD DVD disk. But if it is correct, you know that every single bit in these few gigabytes of data are correct. Because if just single bit will change in this gigabyte of data, hash value will be completely different. And also, these who are not experienced may use hash function as some kind of encryption. For example, you get some password, and you can send it through hash function like MD5, which is okay. So I say echo apple, oh, what's that what I want to say, without appending line break at the end. And then I make MD5 sum for it. Yeah, you should write properly. Okay, after 10 attempts I did what I wanted. And it looks like an encryption, because this is easily readable, this is not easily readable at all. But what you may forget here is that everybody who is not lazy may create a table for all standard inputs to standard outputs. And one more thing is that if you do reverse operation for this hash function to input, so in this direction from input to hash value it's quite easy to do. But if you know particular hash output and you want to know what kind of input was used to get this output, then using just algorithmus hashing is very time consuming. So also a good hash function does following, that this direction is easy and this direction is hard, very hard. So that means in theory, if you do not know what kind of data were used to get this hash, then getting back in general means brute force attack. You just need to do billions of operations to check what kind of particular input produced this particular output. But what is not hard is that you just do few gigabytes of data with pair of input and output. And sometimes these are called rainbow tables. But in general, you can't use this as an encryption, because everybody who is not lazy stores such tables for you to know. So and nobody tries to do this full brute force approach to get from this cache back this particular input. But what they do, they just check, is this one of these hashes where input is already known. And similarly, you can do other hash functions like SHA-1. Some is used for git. And again, you just search for it. And here it is. And you may create more and more longer hashes. For example, there is SHA, where 256 bits, or how many bytes, divided by 8, are used as output, and also there is SHA 512 some. But it's still, if you know, if it's one of these hashes, you can do. How do you use hash for encryption if you want to use? So it's out of collections, but it's important for security. Proper way to do hashing for encryption is to add so-called salt. And here is my password for my computer. From here till here, I think, in base 64 encoding. So base 64 encoding is more compact than hexadecimal, because for hexadecimal you need 2 letters or 2 bytes to show just one single byte. But for base 64 you need 3 bytes to represent 2 bytes. But encryption is done in such a way that it doesn't hash just single password, but it hashes single password mixed together with this random number, also represented as base 64 encoding, together with my encryption. So if you use your hash for encryption, you do following. Here is your input, like password. But before you calculate hash, you delete it with so-called salt. And salt again is diluted for your input in proper way that if you have many bits in input, let's say 8 bits, for input as a password, and you have 8 bits as a salt, then each of these single bits of salt is mixed together with this input in such a way that probability that these bits will be changing to opposite is again 50-50% chance. So it's not something like string concatenation, etc., because it's not secure enough. And if input is longer than salt, then of course you repeat this salting many times for several blocks, and you use output of previous to mix it all together, and only then this mixed input is hashed, and you get proper output here, and you see something like 1, 2, 3. And to check that your password is correct, what do? You put your password, you know what salt is. Salt, for example, here is 3, 4, 5. And you check that it produces 1, 2, 3. And so for encryption, properly encrypted things are always following. Here is hash value, and here is random salt value. And because this is base 64 encoded, how many bits do we have here? 16. So that is, it actually is 1/3 daļa. Approximately 10 bytes of data, and so you need to get, for example, my password back here. You need to check with all possible combinations of salt here, starting from 0000 till to z, or whatever is last character in base 64 encoding. And that of course takes too much of disk space, and nobody tried to store different kind of values together with salt. And Java has built-in hash function which produces 4 bytes in output. So for security it's not too much, you can get collisions, but for practice it is usually good enough. And so then when this hash is produced, value is used. So here is your value or key and value. So for key you create hash, and hash is always single length of number, I think 4 bytes in Java. That means you can always create table here where you can navigate easily and you sort them by hash, and then from here you get this hash value, and then you have reference to the data, and if data happens to be string, then of course you have string definition and array of bytes sooner or later after that. So this is your index entry, how you navigate using hash value of key, and then you get reference to actual data to retrieve this arbitrary data. And that's it about. There are other implementations for map, but I don't remember because these are not so widely used. Now about lists. So list takes only one single date as an input, no key and value, but just value, and you can implement in different way. The simplest implementation is array list of this interface, and array list is list which contains array. So if I have array list class here and I create array list object, so of course it refers to this definition of the class, and here it has all the methods add value, remove value, find value, blah 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 blah. But inside it has, when you create object of array list, it will create array, and of course array will say I am object of array class, and if for example this is array list of string, then it will say the type of this array is string, and it has, let's say, three elements inside it, so there's 3 references to the strings, and here you will have another string which will have array of bytes as actual value. But if it's just array of primitive types, you will get these values of primitive types eventually. So what is good about array is that if you do not count these few bytes as a header of an array, which says I'm array, I contain this kind of data, number of elements is here, then for primitive types you just put elements after elements without any delimiters at all, because you know size of them. If it's integer, 4 bytes, if it's char, 2 bytes, if it's byte, 1 byte. So you do not have any memory overhead. If these elements inside array happens to be object, then here you have list of references to the object, which is fixed size, and then of course they refer to actual data for this object depending on what kind of object it is. And so good thing about array list implementation is that it is a most compact way to hold your values. What is not so good, remember, is that even though in array list you have method to easily add something in your list, what will actually happen is that here you have one array with elements, and when you need to add another element here at the end of list, because arrays are not resizable, everything here will be copied from smaller array to larger array just to add one single cell here at the end or somewhere in the middle or whatever. So that means every time you have add, remove operations in this array list, if it will be large, it will be very slow. So that is bad thing about arrays. So good, you can use array list for implementations if you are not changing this list frequently or if it's small, but you shouldn't use this if it's large and is modified frequently. For that you need to use linked list. And linked list is different animal. for linked list you have links of elements. So here you have elements like if it's primitive type actual value, if it's not primitive type, then it is reference to actual value. And then it has two other references. Next element, previous element, next element, previous element, next element, previous element, here, next here, previous element, next element. And for example, this will refer to that, 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 and this will refer to that, and this will not refer to anything. It will have null here, and for last it also will have null here. And if you need to add new element here, you add your value. If it's primitive type, here is value. If it's not, here is reference, and actual value is somewhere else. And what you need to update, you need just to say if it's somewhere in the middle. You say that this now will refer to that, and this will refer to that, and this will refer to that, and this will refer to that. So you update just 1, 2, 3, 4 links, and you are done. And then you can just jump from place to place inside virtual memory to get these linked lists. So what is bad? Bad thing is that linked list is approximately 3 times bigger than array list because of these references. But good thing is that you may have thousands of elements inside linked list, and adding new element will be just few operations. And therefore you always should use linked list if you have many elements in collection and you need to change them frequently. What is big? Remember that when we talked about string and string builder or buffer, string builder, then size for string builder, initial size for string builder is approximately 4 kilobytes. So that means if you have few kilobytes of data for your strings and less than few kilobytes, nothing bad will happen if you will use just strings. And similarly, if you have just few hundreds, maybe few thousand of elements in your array list, which you are not changing frequently, it will work fine. But if you will have many, much more than few thousands, and you will change them frequently, then definitely you can't use array list, because array list is just nice API around arrays. But linked list will be much more proper way to do. So then set is the interface which allows you to store only unique values. Duplicate elements are not allowed, and you may store also one null element inside it. And it has different implementations. Hash set is the same approach as I told you about hash map. Only difference is that actual value is hashed and then stored. So for hash set, you work in following way. You have some value and you create hash for it. And then you put hash in table of these hashes. Of course, you can show table as a long string of hashes, or you can put it as a two-dimensional thing, but these are just hashes without any delimiters, without anything, because you know length of hash is always the same, and if you want to get sixth hash, you go to the sixth shifted memory to get this value. And then after this hash, there is reference to actual data. If these data are primitive, I think it's put immediately inside hash value, inside the index. If this is not primitive type, it's string, then it actually refers to actual data, where actual data are whatever type of value you had as an input. And Problem for hash set is that they are not sortable because they are natively sorted by hash value, but hash value looks like a pseudo-random number, and that means your values are somehow ordered in strange order, which looks like a random order. And what can you do? You can do two indexes. You can use hash to check for uniqueness and also linked list. So you actually have two indexes, hash values, linked list, and actual value. And that means that the linked hash set is approximately, this index is approximately 4 times bigger than just a hash set. So that's not good. If you don't like this, you can use binary tree set. What is binary tree? Binary tree is index of values where in difference with linked list you had reference to next element and reference to previous element, but in binary tree you have reference to bigger and reference to smaller. So you start with some value, you compare it like bit by bit because it's binary tree. For example, here is some string, you just read it bit by bit, and you check starting position. Here you maybe saw something like 0, 0, okay, 1, 1, 1, 1, 0, 0, 0. You have 0, 0, 0, so it's bigger, so it should be somewhere here. So actual references look similarly to linked list, but navigability is different. For linked list you can easily start from beginning, go forward and from the end, but for binary tree you start in the middle, and binary trees usually are shown as trees with these values. And why tree is important? Because tree is important that for linked list to search particular value you have to go from the beginning till to the end. And of course you do optimization, you do jumps. Oh, it doesn't escape from this. And you use the jumps by divide by 2 approximation. So here is your index. You said jump here, then jump here, until you, because then number of jump is approximately natural logarithm of number of elements here. But for binary tree, you don't need to calculate lengths of your jumps anymore. You just need to compare, is this bigger or smaller, and then jump without any calculation of lengths. You just decide jump left or jump right, or smaller or bigger. So this means in this case binary tree is better. What is not so good is that you need to spend more data managing binary tree, because the worst case scenario for binary tree is that it's actually like linked list. And you start with some very large value, but your beginning position is very small value, and you compare it, needs to be bigger, 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 needs to be bigger. And what you actually do, you go through all these possible elements. That means number of jump is not natural logarithm of number of elements, but is the same as number of elements. So, and therefore, starting position in binary tree always needs to be managed. So this binary tree index should be balanced. That left and right parts are approximately in the same size, so that sometimes means when you add new element it takes a little bit more time to manage it, because all this binary tree needs to be rebalanced. It's not very time consuming operation. In low level programming courses you may try to revert binary tree or balance it, like when you do advanced data structure algorithms, but that's need to be considered. Usually I tend to use binary tree set, which is called tree set, because it's smaller in size. Because I don't like linked hash set, which has both structures to hold hash value and also to hold index for these links. But it's just my preference. You may study by yourself in more details how to decide which to use. But if I need sorting, if I don't care about sorting, hash set is good enough, because some of hash functions are accelerated in hardware. If I need also sorting, then I think tree set is better than linked hash set. So, how do you handle elements in collection? You usually create variable with type of interface, so more general type, and then you create constructor with class which implements this interface. Why it's recommended way? It's not so important anymore, because we have great possibilities to refactor our code, but it's just a polymorphism approach. So with this type we say what we can do with this collection, and here we can change it to something else if our requirements are changing regarding to speed, regarding to used virtual memory, etc. And then all these collections may hold Java objects inside them. And if you get a primitive type stored, then this primitive type is wrapped up into its object, like if you store int inside collection, it is wrapped up into integer, or this object-oriented object data structure. And when you try to get it back, again you get just any Java object, and that means you need to downcast it to proper type. Like here, you add, for example, file handler element, and when you get it back from list, you need to downcast it to file. And this is error prone, because for some reason it may be that somebody can add string into this collection, or just Java object, or integer, or whatever. And therefore, for more modern Javas, they recommend to use so-called generics. And in general, generics is parameter for type, or type parameter, as they call it. For example, when I have something like, what's wrong with this? So I have, let's say, method which returns integer, object, and maybe it takes some parameters, maybe in it. So it returns object, and it is type of this method. Return type is object. But to be more precise, for example, to say that this will not be object but a string in this particular case, here we have a problem. If I would say string specifically, then particularly for this collection method, I would need to override it for all possible data types I may have, strings, customers, integers, etc. Because every time I return different data type, it is different signature. So this interface, which allows me, for example, to do, like, I do not know, sorted list, would be overloaded with all possible data types, and that would not be enough, because everybody who is not lazy may create new data types. And then you need to parameterize these returned types, that it may be any kind of subtype of Java objects. And for backward compatibility, Java designers decided that this subtype will be in smaller, larger than, smaller than, and here is your subtype. So this is your general type, which is used as a signature for method, for example, to say that this method will return different kind of objects, and you don't need to overload it with all possible data types, because in this interface it usually says something like this: object and subtype may be any or star. I do not know precise syntax for these cases, but for your concrete class you say that it will return object, but not any kind of object, but only string. And with such a subtype parameter, they avoid this problem of overloading signature of this method for interface. And so in interface it says that this method will return object, like say sort or whatever, and that is only signature what they need to declare. And so such type parameters are used quite a lot, and I think it was introduced in Java 8, but I'm not sure. And it looks like this, that now you have a list which will not allow to store any parameters, but which will allow you to store only file system objects. And then you create it like a linked list, and you need to add this type parameter for constructor as well. But with more modern Javas you are allowed to just write smaller than, larger than, so this will be put into that automatically. And then you can add file system objects and you can get it without downcasting. And if somebody will try to put string or integer or whatever in this list, then of course you will get immediate compilation error, not runtime error. And that's good, you will understand that your code is wrong even while you are writing it. And then there are different kind of bulk operations for these lists. I will not touch them in details. And here is reminder about implementations and interfaces. On vertical axis it shows features or possibilities of these collections, like unique elements, sortable elements, priority elements, or maps, which means key and value pair. There is also tree map implementation, hash map and tree map, so here it is reminder. And here are on x-axis it shows implementations. Do it uses cache, do it uses array as an internal data structure, does it use binary tree, does it use linked list or links, or several things at once, like hash and linked list together. And then there are iterators. All these collection elements are iteratable, so you can assign iterator to any of these collections, and then you can iterate through him. What is iterator? Iterator is something like cursor in your elements. You have a bunch of elements here, you assign iterator to it, and then with next you can go forward and get reference to this element. And for example, possibility to iterate is one of these things why in Java you can write for string in collection of strings like arrays, etc. because all these collections, including array, implements iteratable interface. And important part for iterator is when you declare it and assign it, it is before first element, or index is -1. And when you first time say next, it got zeroth element. It's because it's easier to just do say next. And if this list or collection is not sortable, you can only go and iterate through all elements in one direction. But if this collection is sortable, like list, you can go also forward and backward. So any iteratable element allows you to go through all elements from the first till to the last. And it can check, does it has next element, it can go to next element, and it allows you to remove current element. But if it's sortable, There is also method has previous, go to previous, add element in current position or replace element in current position like set. So this is for lists. And then I will just mention queue. Queue is object oriented, either stack or buffer. And when do you need like buffers and when some elements need to be into queue? Usually it's not so important for Java, but it may be also for distributed systems. There are many times when you need to connect some fast running process with slowly running process or thread. For example, if you want to print something on printer, you can prepare all the data very quickly. And here is all your bytes needed to be printed out. But when you print it out on printer, it goes slowly. And in such cases, buffers are very widely used because if you can fill up buffer instead of waiting while printer is done here, so here your computer is busy, and here your printer is busy, but starting from this place, computer may do something else, so it doesn't need to wait while this is ready. Similarly, when you connect two different speeds of networks, it may be in opposite way. You collect some data in packet slowly, and then you can pass it very quickly back all the data to your application. And so in all these cases, buffer is used. And how buffer works, if you look on real life example, buffer is like a pipe where you add new elements in one end and remove existing elements from other end. So you can fill up this pipe and then you can slowly decrease number of elements. If you look how it's actually in Windshell memory, usually one of implementations is two chasing cursors. One cursor is to fill up inside this buffer, and it goes here, 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 and when it reaches this end, it starts from the beginning. So it's like in loop here. And when this insert cursor is immediately behind reading cursor, then buffer is full. So this is right. And then reading buffer is another iterator or cursor which chases this writing cursor or iterator. It reads, and when it's immediately after this writing iterator or cursor, then there's nothing to read and buffer is empty. There are other implementations, but one of standard implementation is following, that you reserve some part in Windshell memory when upper end continues to the lower end, and you write with one this iterator or head or cursor, call it whatever, and then you read with another. And the important part regarding to buffer me is that there should always be times when buffer is empty, because if buffer is not empty, you just add latency, because if there's always full queue, then everything, when you need to interact with something, you will just need to wait while this element goes through the queue. And if somebody makes two big buffers and they are never empty, then it adds just latency. And a few years ago it was considered quite big problems that when random access memory became very cheap, different kind of devices created unneededly large buffers for networking purposes, and it was called buffer bloat problem. But currently I think it's more or less solved. Another thing is stack. We talked about stack already. Stack is used when you jump from one place. Again, I got this, and how do I escape from it? You jump from one place to another, 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 and you need to jump back. And to implement this, you use different pipe. You use like magazine or stack. You add elements and you remove elements from the same end of pipe. An implementation of stack I already showed to you. You reserve some memory here in virtual memory, and when you add new elements, for stack memory for virtual machines, you go downwards from larger memory to smaller, and when you go back, you go back. So you use the same reading, writing head or cursor or iterator to add new elements or remove current elements. And when you have reached this end here, your stack is full, you can't add anything new. When you reach this end, your stack is empty, you can't remove anything from this stack anymore. And remembering stack is quite important, because if you overfill your stack, then you can't go back here and continue. And interesting is that native language also, when people talk, it jumps from jumps to jumps to jumps. For example, here is main topic I want to say to you. Then is some other, let's say, topic, and inside this is another topic. And usually, how do we jump back is from this topic to that topic, and from this topic to that topic. And if somewhere at this place teacher asks you, oh, where was I? Then you know that his or her stack was overfilled. So that's about also similarities about stacks and how humans interact and how they talk and think. So in general, our memory is also quite a lot stack based, not buffer based. This queue object is object-oriented implementation of a buffer, and sometimes also a buffer is called first in, first out, because of this pipe, or FIFO, first in, first out from the other end. And for stack it is called FILO, or first in, last out. Because what went first in, it is at the bottom of the stack, so it goes last out. And if you need to implement this buffer or stack in Java, you use for buffer queue, for stack double-ended queue, because Java designer decided to extend this buffer where you can add and remove elements from both ends. And of course, if you want to implement stack, you just use either first end of this pipe or other end. So I told you already that coding advice is that here you mention type of interface, and only here you mention concrete implementation, because if you need to change implementation, you will need to change only in one single place here. And now about sorting and ordering. You know that for Java objects it is required to use equals method, but it is just first iteration, because if we look on our object, and where is equal? Implementation for equals method for Java object is following. It compares references as a simple primitive types, and it says if this object is actually the same object, so reference is the same, because here when you use operator you always work with primitive types. So this current object is, let's say, downcasted or made just to primitive types. This means it cares about reference to an object, and other object also reference. And if these references are the same, this is the same object. If it's not the same, it's different object. And therefore, you shouldn't be afraid to do something like this here if you like, because that's how equals work for standard objects. So if you do something like object my object and there's nothing wrong to do something like this. Because then I will have just less coupling, because I will do here directly the same as I would do this with equals method here. And it may be surprising results for somebody sometimes, because, for example, and when we run it, we see that these are equal. Why? Because these literal values are stored only in one place when code is compiled, and this reference and that reference actually points to the same actual data to hold this value, and so they are the same. But if we do something like this, then it's not the same anymore, because now inside virtual machine I have two different places to hold literal values, one SS and two SS, and string S first points to this literal value, and then it points to completely new place, because I need to create another new string here. This means I need to create new array of bytes to store more things now, and it now points to something completely different to hold total sum of this literal value and that literal value. And funny thing is that compiler is quite smart, and I think in this case these strings will be the same again. But not. And so why do you need to use equal methods? Because equals method for string works in such way that these are considered equal, not looking by where they are put inside memory, but what actual data they hold. And if they hold two S's inside them, then these are considered equals. So remember that you have to use equals method only if you want to compare them by some specific rules which are actually implemented in this specific object. For example, for string, it's implemented in such way that it compares actual data. So here is equals method for string. First it checks is this the same object, immediately returns true. If it's not the same object, then it compares values. And if values are the same, it still is considered the same. So that's important about equals method. So remember, and when you create your custom object like customer or whatever, equals method is already implemented for you, and it will return true if it's the same object, false if it's different object. And if you are not happy about this, then of course you need to override equals method, for example, to compare actual values. Now about hash code. You may implement your own hash code. For example, if you have different kind of numeric values with different ranges, and this is case, for example, for dates. And you know that if you have day, month and year, days have ranges from 1 till to 31, months from 1 till to 20, and year from something to something. Then very efficient way how can you create hash for these numerical values is to use weights for these numbers, like this will be times 1, this will be times 32, and this will be times 366 plus 32 plus 1 is approximately 400. And so you can create hash in following way. Day by 1 times 1 plus months times 32 plus year times 400, and here will be your hash. Of course it works quickly only for numeric types, but for non-numeric types usually you convert them to string, and for string, of course, the hash method is already implemented. And when you do sorting and ordering, important thing is that you have to describe how you will sort your elements. And to do this, you have to implement a comparable interface. And with this, you have to implement compare to method, and it returns smaller than 0 if this object should be before current object, larger than 0 if this object should be after current object. And this is called native sorting. Native sorting is, or comparable interface, is implemented just once, and when you sort by native sorting order, implementation of this compare to method is used. For complicated situations, you have to sort for different criteria, not only for one. Then you define another interface. You implement comparator interface where you can add all other comparing criteria. For example, to sort by names, by surnames, by salary, whatever you like. But in our practical exercise we will implement only this native sorting. And then you have to be consistent of implementing all these utility methods: equals method, compare to, hash code method, and that's it. So if equals return true, then compare to method and compare method should return 0. So these are considered equal, and hash code for both objects should return the same value. If you will not do it properly for your customized objects, then you may get surprising result when you start storing them in different kind of collections and you start sorting them. That's an important thing to remember. And if you do also non-native sorting, it's not required that compare to and compare returns the same result, because when you implement the comparator interface, it is another sorting algorithm for your object. So any time you have several fields inside your object, you can create different comparators for them to be used to sort for all these different fields in your object. And here we went till to the summary. So you should know now that instead of Java arrays, you actually should use different kind of collections. You may use blah 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 array like array list if you want to make your data small and efficient but probably slow when you will need to manage them. Then you need to know that there are different implementations with drawbacks and benefits like hashing, binary tree, linked list. And then you should know, for example, that all collections are iteratable. You can use iterator to go through them. And you can sort them by declaring either native order implementing comparable interface or any other order implementing comparator interface. And then map is collection to sort keys and values. Any questions or comments on that?